All right, we're looking at our third type of transformation. We've looked at reflections, translations, and now we're looking at rotations. One another way of looking at rotations is we talked about how a reflection is flipping it, a translation is sliding it. Well, with a rotation, the word we're thinking of is turn. We are turning it. Is it isometric? Same size, same shape? Yes, it is. Now, this definition right here is pretty important, but before we do that, let's reflect this, and I'm going to zoom in here. Let's reflect this quadrilateral over the y-axis. So we're going to take our vertices and reflect them across the y-axis. The y-axis being this line right here. So our first point is 1 away, so we're going to put it across 1. Our next one we'll put here. This point over here is 1, 2, 3 from the y-axis, so we'll move it 3 from the y-axis on the other side. And our last point is 4 units away from the y-axis, so we'll put it 4 units away here. We'll connect those dots, and we end up with a parallelogram that looks like that. We've reflected it over the y-axis. Excuse me. Okay, the directions now say to reflect that new image over the equation y equals x, which I'm drawing the line for that equation y equals x. So we're going to reflect this new shape across this y-axis. Well, we're going to take each point and count how far it is. That one's 1.5, so we're going to go 1.5. Just put us there. This one is 1, 2, 3.5. So we're going to have a half, 1, 2, 3. And if this counting confuses you, can always use your chart from your reflections assignment. This one is 1, 2, 3, 4, 5. So we're going to go 1, 2, 3, 4, 5. And then we get 3.5 for the last one, which would put us right here. So however you chose to reflect it, we end up with a shape that looks like this. Excuse me. So that reflection, we've done 2 reflections over intersecting lines. So the definition here, the composition of 2 reflections in intersecting lines can be described by a rotation. And if you think about it, this original shape has been rotated to move to become that shape. Now we did it by reflection, but 2 reflections in intersecting lines can be described by a rotation. You get the same results as a rotation. We're not going to go into detail, but we end up with a 90-degree rotation, and we'll talk a little bit more about that coming up. Okay, so the first thing I want to do is I want to fill out our chart here. Excuse me. Let's fill this chart out first, and then I'll reference it in a minute when looking at each of these individual graphs. Okay, so we filled out our chart, and you will have this chart available to you on the test. Okay, so now let's take a look at our first graph. Oops. Let's zoom in over here. It's asking us to rotate our shape 90 degrees. Well, the shape we're going to use, go ahead and graph these points. Okay, so 2, 7. That's going to be A. 4, 1 is B. And 9, 1 is C. So you end up with a triangle It looks like that. Okay, and we're going to rotate it 90 degrees clockwise. So, according to our chart, a 90-degree clockwise, counterclockwise rotation, we're looking at this. So we're going to take our y, make it negative, and make it our x-coordinate, and we're going to make our x-coordinate our y-coordinate. So let's do that. What we're going to end up with for A, again, we're going to make our 7 our x-coordinate and change the sign, and then we're going to make our x-coordinate our y-coordinate. We're going to do the same for B, so we'd end up with -1, 4, and then we're going to end up with -1, 9. So let's go ahead and graph those new points. -7, 2 would be right here, and that's going to be our new image, which is why we put that apostrophe there. And then -1, 4 would be there. That would be our B. And our C is -1, 9, which would be there. Okay, and what we've done now is we've rotated around the origin 90 degrees counterclockwise. Well, let me ask you this question. Now notice that our chart says only 90 degrees clockwise, only 180 degrees counterclockwise, 180 degrees counterclockwise, 270 counterclockwise. Well, if I rotated a point 90 degrees counterclockwise and I ended up here, what if I told you 270 degrees clockwise? Notice that's not anywhere here. But 270 degrees clockwise would be the same as 90 degrees counterclockwise. So really, 90 degrees counterclockwise is the same. You're going to do the same thing with 270 degrees clockwise. And again, same thing for 180 counterclockwise. If we went 180 counterclockwise and then I went 180 clockwise, aren't those two going to end up the same place? So that's the same as clockwise. And then 270 counterclockwise would be the same as 90 clockwise. So if you wanted to add that to your notes, that'd probably be a good idea. Okay, so we looked at that. That was our rotation of 90 degrees counterclockwise. Let's look at our rotation here of 180 degrees counterclockwise. Graph these points. Okay, once you graph those points, we'll look at the change. B. Okay, so we end up with this parallelogram. Looks like this. We're going to rotate it about the origin. So we're going to go look at our directions for 180 degrees, and we're going to see on our table that we make the x negative and we make the y negative, but they stay in the same place. What do we do if they're already negative? Well, we just change the sign because that's what it means. The opposite of -7 is +7, and 3 would become -3. -2 would become 2, and 3 would become -3. 0 stays 0, and 8 becomes -8. And -5 becomes 5, and 8 becomes -8. So we graph these new points. 7, -3. And we need to remember to label them according to what their new position is. 2, -3. 0, -8. And 5, -8. Now this looks like a reflection or a translation, doesn't it? Doesn't it look like we just slid it down to this spot? But the reason we know it's a rotation is because look at C right here. If it was a translation, then that part would correspond with A, but it does not, because that point is A. It should be C, but because it's rotation, this point rotated all the way to this spot, and D rotated all the way to this spot at 180 degrees. Not a full circle, but a half. Okay, looking at the last one, we've got a 270 degree counterclockwise. Let's use these points for that one. Okay, so let's graph these points. Negative 3, 3 is A. Negative 3, 7 is B. Negative 6, 5 is C. And we end up with that triangle right there. Well, for a 270, our rule says that y becomes our x, and our x becomes our y, but we make it negative. So this is going to change to 3 our y becomes our x, and our x becomes our y, but we change the sign, so we end up with 3, 3. So our y becomes our x, so that becomes 7, and negative 3 becomes positive 3, and our y coordinate. 5 becomes my x, and negative 6 becomes 6 as my y. We graph these points. Make sure you label them as you do it. 7, 3, and 5, 6. Okay, and that's how we rotated this figure 270 degrees counterclockwise, and we can see how that is 90 degrees clockwise. All right, next page. Okay, these figures, we are rotating it about the point that's given to us here. So this is going to be rotated 180 degrees clockwise. So it's going to go in this direction 180 degrees. And when we do that, we're going to rotate each point about the origin 180 degrees. So for instance, this point, 90 degrees rotation would put this point here. 180 would put it here. So once we get one point, we can now draw the rest of the figure. And there you go, that's it. Now if we were to go the other direction, 180 degrees, we already kind of said this, but it is the same, isn't it? If I go 180 degrees, we end up with the same shape. So that's a counterclockwise rotation of 180 degrees. Okay, these other figures here, we're going 90 degrees clockwise, so this end point, if I rotate it 90 degrees, is going to be up here. Well, once I know what one point is, I can draw that rest of that figure fairly easy. And on our D here, we're rotating it 90 degrees counterclockwise, so this point would be rotated to here, and then we can just draw our shape from that. Okay, of course that wouldn't be part of it, it would just be that. Alright, let's look at the next one. E, we're rotating this 270 degrees clockwise, so we're going here. This would be 90, 180, 170, so the point would be there. We're going 3, so that's what that would look like. Of course, minus my circle there. 360 degrees, we would rotate it till it fell right back on itself, and we would actually get the same image. And on G, we would rotate that 180 degrees. And if we did that, well, you know, an N is the same upside down as it is right side up. We actually would get the same image as well on that. And if we rotated this square, it looks like a rectangle, but it should be a square. But if it was a square, rotated at 90 degrees, we would end up with the same image. Okay? And that kind of leads us into our next page, our last page of notes. Okay, so here we're going to talk about rotational symmetry. The smallest angle that maps the figure onto itself is the angle of rotational symmetry. For instance, this angle right here, we rotated it to this point. That would be a 90-degree rotation, because that's a fourth of a circle. That would show that it has rotational symmetry. When we can rotate it, and it will map itself. Look at our first example, this isosceles trapezoid. If we rotated this and rotated it a full circle, it would never map itself until we went 360 degrees. If that's the case, then as far as rotational symmetry goes, there is none in that one. On C, this parallelogram, if we rotated it so that this point was rotated to here, that would be 180 degrees, a half circle. That would have rotational symmetry. What would the angle of rotational symmetry? Well, I just said it. We would rotate it 180 degrees. And this regular hexagon, if I rotated it from here, it has rotational symmetry. If I rotated it to here, it would map itself. Well, the tricky question is what is that angle measure? The other ones are easy when they're 90 or half of a circle. But this one, what we have to do, it's a hexagon. It has 6 sides. So it's going to have 6, what we would call what the order is, it would have 6 different places that it would map onto itself. So if it has 6, we divide one full circle, 360, by 6, and we get 60 degrees. So it has rotational symmetry. The angle of rotational symmetry here is 60 degrees. Is it possible to have rotational symmetry but not have line symmetry? Well, look at C. That had rotational symmetry, 180 degrees. But can we draw a line that makes that to show that it has line symmetry? We cannot. That means that yes, it is possible to have rotational symmetry but not have line symmetry, such as a parallelogram. Okay, look at the next question. A student claims that the figure has rotational symmetry and that the angle of rotational symmetry is 360. Basically, they're saying that they turned it 360 degrees, it mapped itself so it has rotational symmetry. Well, 360 degrees rotation takes it back. It is the original figure. Sorry about that spelling. Therefore, there is no rotational, I'll abbreviate that, symmetry. Again, it has to be less than 360 degrees. What does your answer for the parallelogram tell you about its opposite angles? Well, we said that 180 degrees rotation, that means this angle is the same as this angle. Basically, we're saying that opposite angles are congruent. Opposite angles, they're congruent. Now, this question asks, what rotation about G, meaning around the center point G, maps A onto C? Basically, that right there. Well, first we need to know the order of rotational symmetry. How many times will this shape, by rotating it, map onto itself? It has 6 sides. Therefore, 360 divided by 6 is 60. The order would be 6, and each rotation is 60 degrees. So to get from A to B, would be 60 degrees. From B to C would be 60 more degrees, which would make that 120 degrees. A clockwise rotation of 240 maps F onto, well, if we rotated 60, 120, 180, 240, that would leave us onto B. And I'm sorry, I did that counterclockwise. So let's do that again because it asks for it in clockwise. So we're going F clockwise for 240, 60, 120, 180, 240. The answer would be D. Okay, how many degrees would a regular octagon, 8 sides, need to be rotated to carry on to itself? Well, we need to know the order there. If it has 8 sides, that means the order would be 8. So we take 360 divided by 8. And we get 45 degrees. So turn it 45 degrees and it would carry it onto itself. And the order of rotational symmetry there would be 8. Okay? Point symmetry exists if a figure can be mapped onto itself by rotation of 180 degrees. The parallelogram we looked at up here, this one has point symmetry because if you rotate it 180 degrees, it maps it onto itself. The hexagon, this one, we rotate it 180 degrees, it would map it onto itself. So yes, it has rotational symmetry as well. And they give you some examples here. You rotate this 180, it maps onto itself. So these are all examples showing point symmetry. Okay, these are all the notes for rotational symmetry. Hope this helps you on the assignment.